talk about physical properties and get into some basicity here before we look at our reactions. All right, so small amines are water soluble, right? They contain nitrogen, so we have hydrogen bonding on them, so that helps them be water soluble. If you get 6 carbons or so, 5 or 6, greater than that, then you start entering into a realm where the nonpolar nature of the carbon chain outweighs the polar character of the amine, the nitrogen connected to the hydrogen. And of course, like we saw before, branching increases the solubility. Side note is most amines smell like rotting fish, so they're very stinky. And if you've ever been in a lab or if you ever have a chance to work with them, you'll recognize this very, very quickly. One of the things we can do is we can reduce the odor by treating it with an acid. So let's put in a good reversible error here for equilibrium. Now what happens is you have an amine, which is stinky, right? It's a base, and you treat it with something like a weak acid, acetic acid. You get a protonated form of that amine, and that becomes more water soluble. And if it's more water soluble, then it's just making its way into your nose a little bit less. Well, here we saw nitrogen as a base. So let's talk for a second about basicity. So it turns out that the trends in basicity follow the trends that we've talked about all along for acid and bases. So the stabilization of our conjugate acid makes the amine more basic. So this is opposite of what we talked about for acids, right? For a strong acid had a stable conjugate base. Here's a base, so we're looking for a stable conjugate acid. So they're flip-flop back and forth a little bit. So remember that these carbon groups, they donate electron density to nitrogen, which increases the density of the lone pair, right? And that increases the basicity of the amine. And so if you have your nitrogen here with its lone pair, remember that lone pair, that's the thing that's going to make a bond with hydrogen, right? So the lone pairs are the basic part, right? So the more available those are to make a bond with H, the more basic we are then, right? So if you put on here an R group, another R group, and then a third R group, then each one of these R groups in essence donates electron density to that lone pair through induction and makes that lone pair stronger or more available to make a bond with a hydrogen atom. So when we look at this table up here at the top, this is the way we can look at this. So we're talking about pKa. So we could look at pKb's, but we've been looking at pKa's for so long that we'll just stick with those. So remember up here we have less basic, right? Going down here to more basic, right? So a lower pKa means a stronger acid, right, or a weaker base. So 9 compared to 11, that's a stronger acid or a weaker base, less basic, right? Okay. So as we go from that first structure, NH4+, which is our NH3 as a base, if we add an R group to that, then we get a little bit more basic, right? And we're more basic again because we're donating electron density to that nitrogen. Right? And then let's just jump down here and look at 2. So if we throw 2 R groups on there, then that basicity increases a little bit also. Notice it's not going from 10 to 15. It's a small change. Now, what happens in the middle here when we have 3 R groups on the nitrogen is that the ion there is tougher to solvate. So that just makes it a little bit less basic. So it's tougher to solvate and is therefore less stable, and basic. So that's the only one that doesn't follow the trend perfectly there. So if we look at aniline, remember aniline has a structure that looks like this. Of course, we know that there's resonance here. So we're not going to draw them all, we'll just draw one. So one of those resonance structures would look like this with our nitrogen, our plus charge, our minus down here, and this, and then we'll just write here, etc., right, plus the other resonance structures. Now, because that lone pair is tied up in resonance in that ring, it simply makes it a little bit less available. So the pKa of this is 4.60. Right? And that, when we're talking about that, we're looking at this, right? NH3 plus. So that is a stronger acid, right, with a pKa of 4.60. If we compare that to NH4 plus, that had a pKa equal to about 9.26, call it 9.3. So when we compare our pKa's to each other, this higher pKa means that we are a weaker acid and a stronger base. So this is a stronger base, and this is a weaker base. Right? Here you have a stronger acid, and here you have a weaker acid. All right? Other example here is Perot. So with Perot, we have a lone pair here, and this is even more exaggerated, right? Because when we gain a proton from H3O+, we destroy the aromaticity. So this has a pK of -1. It makes it a pretty strong acid, and therefore a fairly weak base. The last thing that affects our basicity here is hybridization. So remember that the more S character we have in a bond, the more we hold on to the electrons that are in that bond. So if we look at a little trend down here below, so here we have a ring with nitrogen in it, lone pair in H. So that nitrogen is sp3 hybridized. So what percent S character is that? It's 1/4 or 25% S character. Right, and then let's talk about pKb's here just to change it up a little bit. So the pKb of this is 2.88. All right, so then if we take a look over here and we look at a nitrogen in a similar type of environment, but let's make it sp2 hybridized. So here nitrogen is sp2. That means 1/3 or 33% S character. And then when you look this up, you'll see the pKb of this is equal to 8.75. Right, so a lower pKb means it's a stronger base. Right, and then pulling over here, looking at triple bonded nitrogen, we'll have to go to a nitrile. So this is sp hybridized, 1/2 or 50% S character. And then when we look up the pKb of this, you find it's 24. So the trend over here is a stronger base going over to a weaker base.